I wish to thank to Hugh and Dan for putting together this wonderful symposium series, and also allowing me to present and hardcore computational guide to present fine organic community. Thank you very much. Today I'm going to talk about is actually mostly it's a multidisciplinary effort to understanding complexity in CH functionalizations. And modern problems of science and engineering, as usual, involve multiple components which are working together in coherent and ways. For example, today it's average chemical reactions includes catalyst, co-catalyst, substrates, additive base, even lights. In order to improve performance of existing technologies and their broad application and designs in new and effective strategies require really it's a deeper understanding the role every component of the reactions. In its turn, this requires actually complexity, a multidisciplinary approach. Today, computation is one of the most effective, extensively utilized approaches. Our colleagues use computation either to explain their experimental finding by purpose to improve their experiments, develop more effective predictive rules, or for designing of novel and more effective technologies. Of course, increasing complexity of the processes which we are dealing with, and also requires a new computational methodology developments. My group at the Emerson Center of Emory University use all available computational methods in a collaborative way with our colleagues, as well as develops the new theoretical approaches to complex problems if that necessary. In order to demonstrate scope of my group's collaborative efforts, let me show you it's two from several projects. One of these projects, which we are collaboratively working with my colleague Craig Hill and Tim Leon, relates to solar to chemical conversion. And here we intend to design a new nano device as well as water oxidation catalyst to split water and to produce either H2 molecule or to CO2 to reduce CO2 to carbon-based fuels. Another project, also multidisciplinary, and involves scientists from the Brookhaven National Labs, Army Lab, and Virginia Tech. And we intended here to design these hybrid materials, MOF and POM-based materials for filtration and multifunctional filtration and decontamination of the warfare gases. Both of those projects, involve multiple interfacial electron transfer processes. Unfortunately, its computational techniques today are not there. Really, it's effectively and accurately to deal with interfacial electron transfer. For these purposes, my group also is developing interfacial electron transfer hybrid interfacial approaches, hybrid molecular orbital molecular mechanics approaches, and really it's including the Koshel quantum dots and quantum rod type of approaches, systems. After this short survey today, I wish to demonstrate the importance of the collaboration between computational and experimental scientists for selective CH functionalization. Project which I will discuss are part of our ongoing collaboration with either members of CH Functionalization Center or it's with center's collaborators. In general, my group tremendously benefits from the established collaborative culture within the center and works to elucidate mechanisms and of the complicated stereoselective CH functionalization reaction, as well as design predictive rules, or it's more efficient and less expensive catalyst for CH functionalization. Just recently, our groups, in collaboration with Jin-Kuan Yu groups, have established key mechanistic details of palladium catalyzed CH bond iodination reaction. These efforts led to prediction and validation of novel CH bromination reaction, as well as to design new nickel-based CH functionalization reactions. Collaboration with Ken Itami groups and actually led us to predict the new kappa-based catalyst, as well as selectivity, predictive regioselectivity rule for kappa-catalyzed aromatic CH amidation. And computation was instrumental on establishing unprecedented role of base in CH activations, or in general, it's in the chemical synthesis. Namely, we, in collaboration with Professor Ken Itamiguro from Nagoya, have shown that intermediate form cluster type of complex between pivalate, cesium carbonate, actually active catalyst of the CH-CO cross-coupling reactions developed by Ken Itamiguro. Our computation also provided clear assistance to Professor Huey Davis' group on their effort in designing of catalyst library and predictive model for regio, diastereo, and selective CH bond functionalization for alkanes and alkyl compounds. Unfortunately, today, it's because of time limitation, I will not able to discuss these projects in more details. Instead, I will demonstrate impact of computation, a multidisciplinary effort to this is a mono-N-protected amino acid ligand-mediated palladium-2 catalyzed and selective CH functionalization, which is collaborative with Professor Jin-Kuan Yu's group. During the last 50 years, palladium-catalyzed cross-coupling strategy has revolutionized field of organic chemistry. Power of this reaction actually comes from the reactivity of the palladium to aryl or palladium to alkyl complexes. Inspired by these findings, our colleagues last 10-15 years worked to develop the palladium-2 catalyzed directed CH bond functionalization methodology. One of major challenge of this methodology is to design suitable ligand scaffold which can coordinate to palladium-2 species and stabilize it. Jin-Kuan Yu groups actually have found that simple mono-N-protected amino acid ligand can be one of such kind of ligands. And his groups extensively use these ligands to develop the selective CH bond alkylation, amination, or borylation, and more. But since it becomes evident that for improvement of these catalytic processes, it is necessary to deeper understand and role protecting groups as well as this mechanism of these reactions. For this reason, we combine our effort to study palladium-2 catalyzed CH bond alkylation in the benzyl hydropyridine substrates. Amazingly, this extensive computation have shown that my MPAA ligand plays multiple crucial roles during the reaction. First, it is actually as a weakly coordinated ligand coordinates to palladium center and stabilized ligand palladium substrate scaffold. Second, it acts as an easy deproton source, which is after deprotonation is amide groups, leads to formation is energetically most favorable and stable intermediate, where MPAA ligands is identically and strongly coordinated to palladium center. And we predicted this intermediate to be the catalytic active species of the reactions. Of course, the next steps which we could expect is as a CH bond activation from here. CH bond activation in this system in general proceeds the concerted metallation-deprotonation mechanism. But it's very complex process, depends on experimental conditions, as well as may proceed two different pathways. In early 2012, we have shown that is actually one of these pathways, which we call external base assisted pathway, is really could happen in experimental condition with high acid concentrations. And in early 2014, we also demonstrated that the internal base could, through the protecting group, could also act as a deprotonating groups. And as you can see from calculated energetics, both external base and internal base assisted pathways leads to energetically to more stable R stereoisomers, which is consistent with experiments. But internal base, this pathways barriers for internal base pathway slightly smaller than for external base pathways. I should also point out that I should also point out that other and wonderful experimental and computational studies from Professors Donna Blackman's group, and Yundong Wu groups, as well as from Ken Hauk's group, Professor Ken Hauk's groups. These experiments and computations are provided a consistent picture. After elucidating the mechanism of this reaction, postdoc in my group, Dr. Brandon Hines, with his deepest analytical computational organic skills, decided to make one more step forward and use these mechanistic details and predict asymmetric general and asymmetric induction model for this reaction. But in fact, this model is applicable to any asymmetric induction reactions, of course, with right tuning the reaction conditions, where active intermediate should have same geometrical motif as the active intermediate in the MPAA ligand mediated palladium catalyzed C-H functionalization process. Namely, and it should have the strongly identically coordinated ligand to metal center with chiral center, with chiral center, as well as a substrate which is also should be identically coordinated to metal center. And the substrate should have the chiral and tetrahedral carbon center. This in order to apply this model to elucidate selectivity for MPAA ligand assisted the palladium catalyzed C-H functionalization, we decided to proceed. This actually is a roadmap which is to come from this extensive literature data. Mainly, first, understand mechanism of the reaction, which we already did. After then, identify selectivity-defining defining transformations. Then, the selectivity-influencing factors. Then, combine all this knowledge and calculate the EE of the reactions. And we apply this extensive analysis first to identify selectivity-defining transformations on this system. We find that this actually one of these transformation is a substituent inversion process. And this process, base of this process actually is the exchanging of position C2 and R3 ligand centers of substrate. This may also be defined as a choice between activating C1 and C1H and C2H bonds. Another the transformation which we find is a Chelate inversion transformation. And this transformation based in the positioning of directing group of substrate to either trans or cis is the donor group from the ligand. And second concept, second step as for the roadmap which we developed is identifying selectivity influencing factors. And for this reason, we find that actually it's one important factor is conformational flexibility rate. But this is not only one. Another important factor is interaction between ligand and substrate, which is could differently impact to transition state for R stereoisomers formations or S stereoisomer formation transition states. Third factor, which is a gearing effect. Gearing effect defined as an interaction between bulky R ligand substituent of MPAA ligand and the protecting groups of this amide group, center. This control palladium plane where CCH functional activation process takes place. I should mention that previously the GRN effect was proposed or extensively used by Professor Yun Dong-Woong groups. After that, we spent some time analyzing the factors controlling actually Chelate inversions. We find that the Chelate inversions is not just trans-cis isomerization process, but it is actually also important availability which protecting groups is which actually it's the base is going to be involved to CH activation process. For example, if directing groups is located in transposition to amide center, then protecting group from amide becomes available for CH deprotonation, which is actually a very favorable deprotonation process. If it is cis position, then the carboxylic groups is should be involved to the deprotonation step, which is not really a favorable process to go. Based on this analysis, we predict that this actually MPAA ligand controls Enantioselectivity reaction not only by trans effects, but also by fixing position of internal base on only one side of the catalyst in the catalytic active intermediate. I should mention that in all my discussion here, position of chiral center of the ligand is fixed to be its up position from the palladium plane. If palladium position of this chiral center is going to be down position, then it brings a different type of Chelate effect and may actually GRN effect may actually impact to the selectivity loss. In fact, our analysis shows that there are several channels for selectivity loss. One of them is partial ligand dissociations, from bidentate coordination to monodentate coordinations. And this strongly suggests that a stronger coordination ligand is required for selective, highly in the selective reaction design. Second is, as I mentioned, this ligand chiral center conformational flexibility. And based on this analysis, we predicted that fixing the ligand conformation is an important factor for the development of highly selective highly selective reaction design. After doing all this analysis, we decided to apply to our findings and to their reaction, which we've been actually tuning for, and calculate selectivity of the reaction. I should mention that here we use this very different approach than in literature. It's extensively other researchers are using. Basically, we calculated all transition state and then calculate an enantiomeric ratio using Boltzmann distribution for all these transition states. We find this reasonable agreement with experiments. It is 87% versus 79%. After getting this agreement, we decided to test the predictive power of this model to see if this model can predict, for example, increase selectivity by replacing the MPAA ligand with actually the MPAA-HA ligand. This reaction was previously reported by Jing-Kwan Yu. And this is a desymmetrization, this is one-to-one substituted cycle of butane by using this alkylation reaction, by using these two different ligands, MPAA type of ligands. For this reason, we actually calculated all transition states. And here, I just want to show two energetically lowest selectivity controlling transition states. As you can see, R transition state energetically slightly more favorable than its S transition state, and also its calculated selectivity is very low. In another way, in an MPAA ligand failed to control the selectivity of these reactions. Major analysis shows that this is this failure because of the lack interaction with, between this ligand and substrate. we could expect that is a replacement carboxylic acid by the methylhydroxamic acid could actually improve these interactions or to bring more interactions. In fact, we see it is indeed this increased energy difference between these two transition states, as well as improves the EE. But because of this geometrical flexibility of methylhydroxamics, it's at the transition state, it flips in order to wants to avoid interaction from the ligand substrate. And this analysis actually predicts that if we can replace for a methylhydroxamic group with conformational more rigid one, we could get the better selectivity of the reaction. When we come to this conclusion, actually, Jin-Kwan-Yu groups has published this paper, CH bond borylation on the same desymmetrization on these cyclobutanes in the substrates. And indeed, they show that going from this methylhydroxamic groups to aminomethyloxazoline, it's to improve selectivity to 99% of the reactions. And our calculation, it confirms this indeed, we also get 99% selectivity, and the energy difference between these transition states becomes even larger. I believe that I hope that I was able to convince you that we predicted really, we are designed really, it's a general selective asymmetric induction model with presented here geometrical framework or geometrical scaffolds, as well as with this model can be applied any kind of organometallic reactions, CH activation or reaction, but we need to really tune this before to applications. We also came up to the factors controlling this MPAA ligand mediated palladium to catalyzed C-H bonds is functionalization and selectivity of these reactions. Currently, we are utilizing this model and to design more novel chiral ligands and synthetically more desirable substrates. And at ends, I would like to thank to my group, especially it's Dr. Brandon Hines, Dr. Travis Fig, and as well Dr. Hyung Zhu, who contributed strongly to this project. And my collaborated from the CH Functionalization Center, Professor Hugh Davis, Simon Blakey, and Cora McBeth, Jin-Kwan-Yu, Richmond Sarpent, and Jared Lewis, and all system, Donna Blackman, John Berry, all the CH Functionalization Center members, as well as my collaborators from Nagoya to Professor Itami and Murakami. And I wish also thanks to the funding agencies for this specific projects. The funding came from the NSF. Thank you very much for your attention.